Alrighty, so we're going to do a few more examples from infinite sequences and series. So we're going to talk about a few more limits and then get into some of the series parts. So just a kind of a wrap up from what we were doing in the first part of the notes here. So when I look at limit statements like this, I want to be able to, again, sort of walk through where's the highest power located, where is that? Because the biggest power, the fastest growing, is going to affect much more so what's happening in our limit. So in this case, my biggest degree term is n to the third, and it's in the numerator. So think about that as we look at what happens ultimately when we do our limit. So I'm going to do the algebra, and again, I'm showing way more than probably what most of you would have to do, but because it's a monomial in the bottom, I can look at these ratios just one at a time and break this down and just do the division. So I'm doing that division. And I'm going to reduce each of those. So that would be an n squared over 3, 1/3, and a minus 2 over 9n. So I know a lot of you can just jump right to the green. That's fantastic. Now, technically, what we're saying by those theorems for limits is that I can take this entire trinomial and break it down into the limit of each one of those statements separately. So the limit as n approaches infinity for each one of those ratios, and that way I can put the limits together then. So it makes it a little bit easier to do this calculation. I can look at the limits of each part separately. Now, in terms of efficiency, I usually go right from the original statement to what I wrote in green to the answer. But if you need to write each of those limits separately, that's great. That's mathematically accurate, but you may not need to write all of that. So let's look and see. As n gets really large, what happens to each of these ratios? Well, n squared over 3, if n is getting big, is going to get huge. That's going to grow without bounds. So that's going to be infinitely large. It's a quadratic. What happens to 1/3? Well, it's a constant. Y equals 1/3 would be a horizontal line. It does not change. And then the 2 over 9n, n in the denominator, that's going to go to 0. It's just like 1 over n. So it's going to denominator gets big, fraction gets small. We would have been totally fine without that first term, but because we have that infinity in there, this limit does not exist. So again, I'm going to direct your attention back to where the highest degree term was located. The highest degree term was in the numerator. What is this thing going to do? Well, it's going to grow. It's going to get huge. If you graph it, you can see that. You can look in your table. You can see the y values getting bigger. It's not approaching anything, so the limit would not exist. All right, so let's take a look at another one. Very similar to that, another monomial on the bottom. We want to find the limit as n approaches infinity of 4 minus 5n over 3n. So again, I'm going to show the work, and hopefully some of you can start looking at this and being able just to see what happens by your looking at those degrees in the top and the bottom. So I'm going to go ahead and split it up, do the reducing. And again, I know you can do all that in your mental arithmetic here. Can't do anything with the first one, but 5/3 for the second one. And then really what I'm doing then is I'm writing this as separate limits and evaluating each one by itself. So the limit of 4 over 3n minus the limit as n approaches infinity of 5/3. All right, so what happens to 4 over 5 or 3n? Well, the n gets large, so the ratio goes to 0. And what happens to 5/3? Well, it's a constant, so it would go to negative 5/3. So the limit would be negative 5/3. Now, some of you hopefully can recognize that because you looked at the highest degree term in the top and the bottom. They are equal. The degrees are equal, so that means they grow at the same rate. The only terms that really matter then to determine the limit are those highest degree terms. So looking for where those are located really helps. Okay, I want to go back to one that we did not do in part 1. This is an example where we have to deal with an exponential as part of our statement. So if it were just this, I'd be feeling pretty good about how I need to deal with that. That negative 1 to the n thing kind of scares me. So let's start by trying to break these apart so I can sort of isolate my issues. I'm going to write this as the limit as n approaches infinity of negative 1 to the n times the limit as n approaches infinity of n over 8n plus 1. What I'm doing is using the product property. So we have our theorems of limits, things that we can do. So I'm using this product one right here where it says the limit of the product of two things is equal to the limit of the first times the limit of the second. So I can actually break them apart and look at the limit of each piece separately. So I'm going to do that because I think that's going to be easier. Let's talk about this second piece first. Let's do the limit for that first. So I'm just going to kind of sheet over here with my space and do just that second piece. Now this one is a little bit different than the last two that I just did because this one has a binomial in the bottom. So if you have more than one term in the denominator, it's not so easy just to divide because I'd have to do long division, and that's not something that anybody probably wants to do right now. So what we decided that would be the easiest is to make a ratio out of each of these so I can look at each ratio separately. So I divide every term by the highest degree term, whether that's in the top or the bottom, doesn't matter. So we find the highest degree term, top or bottom, or maybe it's the same, and that's what we divide through by. So in both the top and the bottom, I have an n to the first. So I'm going to divide through everything by an n to the first. Now, it's really important that you realize that that this is a way to make it be a way to look at those ratios separately. So we can look at what happens to each of them. And that it's totally mathematically legitimate to do because I'm dividing every single thing by the same value. So I can reduce. So I can reduce each of those fractions, and now it's going to be a lot easier for me to say what happens as n gets really, really big. So what happens to 1? Well, it stays 1. What happens to 8? Well, it stays 8. What happens to 1 over n goes to 0. So our fraction would go, or our limit would go to the fraction 1/8. So this limit for this part is 1/8 times, now we need to talk about this -1 to the n thing. All right, so we're going to do our work for that over here. So everybody have what you need for this. I'm going to go ahead and talk about the other one. So what happens with -1 to the n? Let's think about what that sequence would do. If n is 1, it'd be -1 to the first, that would be -1. If n is 2, it would be -1 squared, that would be 1. If n is 3, it'd be -1 cubed, which would be -1. If it's -1 to the fourth, it would be 1, and so on. So this guy bops back and forth, alternates sign between -1 and +1, and -1 and +1 forever. So doesn't really have a limit because as n gets bigger, it's not approaching anything. It's going to +1 and it's going to -1. It's doing both. That limit does not exist. So it's going towards plus or minus 1, can't be going towards two different values. Limits have to all be approaching the same value. The word that we use for that, we'll talk about that in another section, is called converging or convergent. It converges. It comes together. So if you're going towards a 1 and a -1, that means if I was multiplying those together, it would be going towards plus or minus 1/8. Can't go towards two separate numbers and have a limit. So the limit would not exist because it's going towards two separate values. So that -1 to the n, the alternating sign really did mess us up for being able to have a limit that exists. Okay, so the rest of what I want to talk about today is sum. So we didn't get a chance to do that in part 1. So the actual concept of infinite series, remember series means a sum. So it's the sum of the terms in an infinite sequence. So here's the thing that's kind of weird. Infinite means it keeps going, ... right? So it's much easier to do finite ones. Those are ones that stop because you have a beginning and an end. How do you actually add up an infinite number of things? Well, let's talk about some of the ones we know about. Arithmetic, that's going to be a no-go for sure. Can't find a sum of an infinite arithmetic. What that would mean is you keep getting bigger and bigger values. So say your sequence is like 5, 10, 15, 20, 25, 30, going up by 5. You're never going to be able to add up all those terms because they keep getting bigger. There's no sums for these. It's not possible for any kind of infinite arithmetic. But there are some kinds of sequences out there, like the geometric ones we look at, that we just might be able to do an infinite sum for because the terms get tiny. So if a sequence has a limit, so like arithmetics don't, that's why we can't do this, but if the sequence has a limit, and not only that it has a limit, that nth term approaches 0 as n equals or approaches infinity, so the limit equals 0, then the corresponding series actually has a sum. This doesn't happen very often. There's only one type of sequence that we're going to be looking at that you can actually do this for. There's only one type of sequence that actually goes towards 0, and it has to do with geometric. So let's talk about that. So the sum of an infinite geometric series. What I have written up here for you is the sum formula for a finite geometric series. Now, to make it infinite, we have to look at what happens as n approaches infinity. So to make this an infinite series, we have to think about what that's going to be doing. So what I'm going to do then is take the limit as n approaches infinity of this formula, this relationship, and see what happens. The only term that has an n in it is that one right there. So I want you to think about what's going on. For all the other terms, as n approaches infinity, a1, the 1's, and the r are constants. They're just values. They're going to stay the same. The only thing that's going to be affected or change is this r to the n. That's the only one that has a value of n in it. So what happens to r to the n as n gets big? Well, it depends on what r is, right? So if the ratio is bigger than 1, what things happen in exponential? That's an exponential expression. If the ratio is bigger than 1, like 2 to the n, what is that going to do? Well, it's going to get huge. It's going to grow. So that means r to the n would approach infinity. So this would not have a limit. The limit would not exist. So the limit does not exist. But what if the ratio is less than 1? Notice absolute value because these signs could alternate. What would r to the n do then if the ratio is less than 1? Well, it goes to 0, so the limit exists. We can actually do it. We can figure out what it is when the ratio is less than 1. So let's do that. If this goes to 0, that means we'd have a1 times 1 minus 0 over 1 minus r. Remember, the a1 is a constant. It's just a number. 1's are constants. R is just a number. It's a constant. So we can get all the way down to a1 over 1 minus r. The sum of an infinite geometric when the ratio, common ratio, is less than 1. And notice the absolute value bars again. It could be a negative ratio, negative 1/4, still going to be fine. Alternating sign, but still going towards 0. So kind of cool. The only type of infinite series we can do, though, is geometric with a ratio less than 1. If the ratio is bigger than 1, game over. No sum because those are going to grow. All right, so let's try a couple and see if you can recognize what's happening. So always take a look and see what kind of sequence or series you have. It's written as a series. This one is geometric. And if you take a look, the ratio would be negative 1/7. Remember, if you're not sure, just take any term divided by the term in front of it, do that division to figure out the ratio. So what does that tell me? Well, the absolute value of the ratio is less than 1. That means it has a limit. The limit exists, it approaches 0, which means this has a sum. So that's kind of my thought process behind this. If it has a limit, it has a sum. These terms get smaller. Basically what we're saying is the terms at the end of these series are so tiny, they don't even add really anything into that sum anymore. If you remember some of the ones we did in part 1, we got things like times 10 to the negative 59th, and that was only term 100. So they are so negligible, so tiny that they don't really change the sum over time. So the sum of this infinite geometric, the ratio is less than 1. I know I can calculate this. It would be 21 over 1 minus the ratio. Be careful that you get those negative signs in there. So over 8/7 we divide, and we end up with 18 3/8. Or you could write that as 18.375. Some people just leave it as a mixed number or an improper fraction, 147 over 8. All fine. So all of these are ways that we can add them up. So basically what we're saying is if you do 21 minus 3 plus 3/7 minus 3 over 49 plus, and you keep going infinitely, you're going to get closer and closer and closer to that value. So 18 3/8. So kind of cool that we can actually calculate an infinite sum. All right, let's take a look at the next one and see if that's possible as well. The dead giveaway here are the numbers getting smaller, or are they getting bigger? If they're getting bigger, we're not going to be able to find the sum. If they're getting smaller, might be able to do something with that. So is this geometric again? Well, double check your ratio. Looks like it's 1/9, right? Remember, we can do any term divided by the term in front of it, so we can double check and make sure that that makes sense. So that means its ratio, absolute value of its ratio, is less than 1. Awesome. That means it has a limit. And because it has a limit, I know it has a sum. Those terms are approaching 0, so the sum exists. The limit exists, then the sum exists. So I can use my A1, 81, over 1 minus my ratio, so 81 over 8/9. And when I simplify that, that would be 91 1/8. Or 91.125. Make sure you type it on your calculator and check. If you prefer, you could even leave it as the improper fraction version. All of those are fine. Now, a really cool application of this is repeating decimals. It's kind of interesting to see how our number system is put together. The number 0.76 repeating is not as easy to, to put into fraction form as you might think. If I didn't have the repeating bar over that and it was just 0.762, nobody would have any trouble with that. So it would be 762 over 1,000. We just just look at what that place value would be. The problem is this isn't just 0.762. The 762 continues infinitely, and that's our problem. So how can we kind of express this in a way that we can deal with? So I'm going to break this that decimal up. I'm going to move this down a little bit so we have room. This was 762 over 1,000. What if we think of this decimal that I just wrote as 0.762 plus the next one would be 0.000762, right? And then plus 0.000000762 and so on. If I added all those decimals together, I would get that 762, 762 over and over again. Well, then that means I can write each of those decimals then as its own fraction. So the next one would be 762 over a million. And then I'd have 762 over 1, 2, 3, 4, 5, 6, 7, 8, 9. So billion. And it would continue forever. And if I think of it like that, take a look. It's infinite and it's geometric. So this 0.762 repeating, all that is an infinite geometric. And what's the ratio? What are you multiplying by each time? Well, it's 1/1000th. And guess what? That's less than 1. So that means it has a limit. It approaches 0. Those terms get tiny, which means it has a sum. And we know how to do it then. We have a way that we can calculate what that would actually be. It would be A1, 762 over 1,000, divided by 1 minus the ratio, which would be 762 over 1,000 over 999 over 1,000. Now, when you multiply by the reciprocal, divide your fractions, the thousands will divide out and you're left with 762 over 999. Now, I want you to try that on your calculator. Divide that out. 762 divided by 999 works out pretty slick, pretty amazing. Repeating decimals are just infinite geometric series. It's something that you've worked with for a long time but maybe never realized. Now we can reduce this, so they are reducible, but I think it's easiest to see the pattern if you think of it from this. If there's 3 places repeating, we're going to have a 999 because you're always going to have this same scenario going on. But what if you only have 2 places repeating? We'll take a look at the next one. I can do exactly the same thing. Some of you might be able to guess if it's 2 places repeating what that might be. But again, I'm going to think of this as a series. So like 0.45 plus 0.0045 plus 0.00045 and so on infinitely. That means it's 45 over 100 plus 45 over 10,000 plus 45 over a million, and so on, right? Keeps going. That means it's an infinite geometric. The ratio is 1/100th. So because that ratio is less than 1, the limit exists, which means the sum exists. It goes to 0. Those terms get teeny tiny. And we know how to find our sum then. It would be A1, 45 over 100 over 1 minus the ratio, 1/100th. Well, watch what happens. You get 45 over 100 and then 99 over 100. So 2 places are repeating and I had a 99. So when I multiply by the reciprocal, again, the hundreds will divide out. You get 45 over 99. So can you guess if 4 places are repeating what your denominator would be? 9,999. What if 1 place is repeating? Then it would be a 9. That's where those repeating fractions or repeating decimals come from. And again, you can reduce. It's 5/11ths, but I think it might be easier for people to look at from those repeating decimal standpoints. So kind of cool the way we can rewrite these infinite geometrics. They're just, it's a repeating decimal. It works the same way. So it's kind of cool that our number system is using things like this. So there's only one kind of infinite sum we can do. It's infinite geometric.